Today we have Team Pathfinders. So the team of 12 are working towards feasibility study and mission analysis of an asteroid mining mission. So the objective is to develop a top-level design of a mission that returns 500 kgs of regolith from a near-Earth asteroid that fills the deficit of a precious minerals on our planet. So for them, I would like to call upon Team Pathfinders.
Hi guys, we're Team Pathfinders, and what we're trying to do is we're trying to have this top-level mission analysis and feasibility study design of a near-Earth asteroid mining mission, and also sample return of 500 kgs ore back to Leo. Yeah, so this is my team, and we are a wonderful bunch of 12, coming from all sorts of backgrounds like electrical, mechanical, space systems, engineering, and things like that. And it's been really fun spending 6 weeks working with them. And here are our lovely mentors, Anusha, Rashka, and Vishnu. And I would like to say thank you for all the effort you've put into mentoring us. So thank you. Yeah, so let me start off with my presentation. So the objective of our mission is to launch a satellite to a near-Earth asteroid within the time frame 2027 and 2030 and return 500 kgs of ore to Leo. So in order to do that, the first step is to select what kind of asteroid we need to go to. So, in order to do that, we decided upon the composition of an asteroid was important to us. The size of the asteroid needed to be around 200 meters. The delta V, required to get to our asteroid needed to be less than 9 kilometers per second. We also consider the inclination values and the number of launch opportunities that we had from 2027 to 2030. So looking at all these parameters, we narrowed down one asteroid from like over 20 asteroids by doing trade studies. And that asteroid is called as 1989 MM. So coming to mission analysis and the concept of operations. So the objective of mission analysis was to select a launch window, to define the initial mission conditions and the delta V requirements for a mission, and to select the different kind of orbits and trajectories that our mission needed to reach the asteroid and back to Earth. So we kind of looked over 6 different kind of mission scenarios. As you can see, the first one was a direct transfer from Earth to the asteroid. The second one used the Earth gravity assist. The third one used the Moon gravity assist. The fourth one used the Mars gravity assist, whereas the fifth and the sixth one were different combinations of gravity assist using Moon, Mars, or Earth, Mars. So the final selection using trade was done, and considering different parameters, and the final mission that was chosen was the Mars gravity assist. So I'm going to go over the CONOPS now. So what happens is the Earth or a satellite is at a parking orbit of 10,000 kilometers around Earth, and it takes a hyperbolic trajectory of Earth departure and then sets off to Mars with a flyby altitude of around 50,000 kilometers. The V infinity for departure and Mars approach are as shown here. Once it's approaching Mars, it takes a flyby around Mars. This basically means that it uses the gravity of Mars to kind of accelerate the spacecraft, meanwhile reducing the delta V required for the mission. So once the flyby is completed, we have a Mars departure, and it takes a hyperbolic trajectory back to the asteroid, which is called the asteroid approach. And the parking orbit around the asteroid is decided to be 10 kilometers. The V infinities are mentioned as shown here. Once the satellite comes closer to the asteroid, it begins its proximity operations. So these proximity operations are to see what sort of environment the asteroid has, and what sort of features does the asteroid have. So the delta V for the proximity operations are 13.37 centimeters per second. Once the proximity operations are complete, the mining operations start, and which we will discuss further in this slide. And once the mining operations are finished, again the satellite takes a hyperbolic trajectory back to Earth, which is called as the Earth arrival. To sum it up, as you can see here, the journey of a satellite starts off from Earth, takes a flyby around Mars, goes to the asteroid, finishes its proximity operations and mining operations, and then comes back to Earth with 500 kgs of ore. So the total delta V for the mission is 1.67. As you can see, the delta V to the asteroid is like 3.62, and the delta V to Earth is 2.67. If these two are added without the flyby, the total delta V would be like around 5 or 6. Because of the flyby, the delta V is reduced by 4.7 kilometers per second. So flyby is a really useful tool for mission analysis. Also, this is the orbital diagram for our entire mission. So next, the important thing was environmental analysis, and I'll ask Srinitya to take over.
Yeah. Hi, this is Srinitya, and now we are going to talk about the environmental analysis of a spacecraft. The main objective is for the selection of type of asteroid and surface properties using the spectral data and checking out the gravity conditions and orbital parameters and the space environment considering the GCR like galactic cosmic rays, albedo, and Yarkovsky effect, and checking out the landing site. And next, we'll go to the analysis of this spacecraft when it is in the space. Yeah, these are different types of effects that a spacecraft is going to face when it is in the space, like thermal variation. When it is in this range, it can cause peeling, cracking, and pinholes. And spacecraft is also going to face like UV radiation, where it darkens the materials, and other radiation effects, and vacuum, where outgassing takes place in the range of 10 power 6 to 10 power 9 torr, and space debris, where it damages the solar cells and with average velocity of 10 km per second. And this is the analysis of the asteroid, where we have selected the type of asteroid is X type, and the ores present are the platinum and nickel ore. Size of the asteroid is approximately up to 300 meter, and its inclination angle is 4.37 degrees, where the analysis of like orbital period around the sun and synodic rotation are also given, and the gravity values, that is 1.98 kilometer per second square, is also given. And we have studied regarding the different effects on the parts of the spacecraft, like optical fibers, transmitters, detectors, like what are the effects that when it is in the space. Yeah, thank you.
Hi all, this is Abhijit, taking up AOCs as my part. Here, the main purpose of AOCs is nothing but maintaining the complete path of the spacecraft in a particular way with respect to its maneuvering conditions and also its overall orbital path. So here we will be having multiple satellite modes. Based upon them, we will having few selections among them, and after that, we will coming to the slew rates and detumbling rates. In the slew rates and detumbling rates, we will be referring with a very slight path, and also we will be having a group set of actuators where we will be considering reaction wheels and the thrusters. Here in this, assuming this is an overall spacecraft, here we can see the thrusters placement, reaction momentum wheels placement, the placements of star sensors and the sun sensors. And coming to the reference frames, the topic with respect to tracking, we will be having three multiple reference frames. The first one with respect to the Earth, where we will be having that geocentric one, and with respect to the cruise condition of our spacecraft, we will be having it at the heliocentric reference path. And considering to the path which is near to the asteroid, we will be having asteroid centric one. Yeah, here we will be considering the velocity configurations where for the spacecraft with respect to the determining path, slew condition, and tracking condition, and based upon these conditions, we are having the refined values of this. Thank you.
Yeah, so moving on to propulsion, the main objectives of the propulsion subsystem would be to select a sort of propulsion technique, which is like liquid, solar, solid or electric propulsion technique, and to come up with a propellant budget as to how much of oxidizer and fuel we need. Selection of launch vehicle depending on the overall mass of not just the satellite but also the dry mass and other things. Then the lift-off mass estimation and the design of PMD and pressure in tanks. So as we can see here, depending from the inputs from astrodynamics, we know that our total delta V is like 1.6 kilometer per second. So we fed it into these Chertkov-Sweet equation, and we got the overall propellant mass required for our satellite from Earth to asteroid and back, carrying 500 kgs of ore. So we selected hydrogen and nitrogen tetroxide as our fuel because based on previous research, because OSIRIS-REx also considered that, and it has a fairly good ISP, and we use the mixture ratio as 0.9. So using the overall propellant mass and the mixture ratio, we found how much of oxidizer and fuel we required, which is shown here, which is 2.4 tons and like 2.1 tons. And using that, we calculated the size of our refrigerant and the size of our fuel and pressure in tanks. So the fuel tanks are pressured at like 20 bar and have a radius of like zero 0.8 and 0.7 meters, whereas a pressure in tank, which is like filled with helium, is pressured at 350 bars and has a volume of around 230 liters.
Good evening to one and all. I'm myself Riya. Me and Akash were handling power. So our main objectives for the whole project was to calculate the power requirements of subsystems and to finalize on the power source as well as the end of life and beginning of life power, and also design the power source, that is a solar array size, and also size the battery. First of all, what we did was we conducted a trade-off study to determine the power source, and we came up with solar array that was the best. That was the best one we could find out. And then we did the trade-off for battery, and we found out that lithium ion would be best suited for the mission. And also we also found out the power required for each subsystems from equations using the referring the elements of spacecraft textbooks and such. We also found out that we also conducted a trade study to determine the solar array cell, and that was found triple junction gallium arsenide was found out to be best. We found the solar array power consumption to be 990.287 watt, and beginning of life power to be 336.24 watt, and UL power to be 83.16 watt. We did different situations and selected the best one out of those. And solar array area, we found out that to be 11.908 square meter, and the mass of the solar array as 9.6 watt per kilogram. Also, we did a little bit work on the architecture as well, and we found out the direct energy transfer system would be best suited for the mission, and a shunt regulator would be used, and the topology would be distributed topology. To talk about the battery, over to Akash.
Yeah, hello all, I am Akash. We have decided to choose lithium-ion battery because of main advantages like high specific energy and more reliability over traditional batteries like nickel cadmium and nickel hydrogen. Also, it will produce more power, and the battery life also more than 5 years, which is essential for a space environment. Also, it can be operated at minus 10 degree to 30 degrees Celsius, which is viable for this mission.
Hi all, I am Kallu Sudarshan. I am handling the communication and OBDS. So in communication, we have did the link budget, selection of antenna, and in OBDS, we did the system interconnections and the data architecture. So all the communication is done through X band, that is from 7.2 to 12 gigahertz. And in the Earth, we will be using DSN, that is Deep Space Network. We have 3 antennas, LGA, SGA, and MGA. 2 LGA, 1 MGA, and 1 SGA. SGA has a gain of 42.5 with an aperture of 2 meter. MGA has a gain of 18.9 dB, and LGA has a gain of 9 dB. So, moving to the OBDS part, we have RAD 750 computer, which is interfaced with the spaceware database. And also one more thing is all the communication it is happening through a link margin of 18.82 dB and DSN downlink data rate of 5.02 dB. So that's all about OBDS and communication.
Hello all, I'm really sorry to say that I don't have web camera, so I can't turn my video on. So myself, Malvika and Arun, we worked on the subsystem structure. And as you know, structure is the stuff that hold things together and provide support. So with the reference to a design approach, a model for our spacecraft was put forward. So firstly, the past mission models were analyzed, and then a qualitative analysis on the whole design scheme from the data collected from respective subsystems were used. So from the obtained data, a preliminary equipment arrangement was done. such as we added the telecommunication system to be installed close to the antennas, and that was to minimize the cable losses. Batteries were arranged side by side with the power control equipment. The communication system were mounted on high plate just below the high grain antenna, and propulsion equipment mounted on or near a tank to configure the system as a separate module. So after the preliminary arrangement, an important factor which considered when designing a structure was the space and the materials that a structure utilizes. So depending on the properties of material that can function in space, Kevlar, aluminium, polymetric composites, carbon-carbon composites were all taken into account. And from all these structural data, a final spacecraft were modeled using a basic CAD design. That was done by Arun. So that's it from our structural team.
Good afternoon, everyone. Myself, Ketan, and I'm handling mining. And the objectives for mining were to conduct a feasibility study of the different mining techniques and different mining architecture, and to finalize on a mining technique, and then come up with the mining operations, and finally with the mass and power budget. And so these were the three different strategies that we considered for this mission. For the first one, it is using a single spacecraft where the mining and excavation head were attached to an arm extension, which was rotatable so that we can have multiple sites within the radius of that arm. And the second one was using a rover once the satellite lands, and the mining is conducted using the rover. And for the third case is deploying mother and daughter satellites, where the mother satellite stays in the parking orbital and the daughter satellites land on the asteroid and they conduct the mining. And coming to the operations, after conducting a feasibility study, drilling was found to be one of the feasible methods for this mission in order to extract 500 kg. So we'll use a drill method, and for excavation we'll use a vacuum suction technique. And we have a 5 kg of ore extraction target for a day. And the total time frame for mining would be like 1 year, which is a minimum approximation. And the total power requirement is around 74.25 kilowatt per month. And in order to anchor on the asteroid, we'll be using the microspine technology, which was used by one of the previous teams. That's all. Thank you.
Yeah, so to conclude, I would say that a satellite travels from Earth, has a mass flyby, goes to the asteroid, does proximity operations, mines for 500 kgs of ore, and then returns back to Earth. And all of these operations span for around 4 years. So the mission timeline is around 4 years. Some of the conclusions that can be drawn from the 6-week internship are that these phase A studies show that this mission is feasible. Other mining architecture concepts need to be explored because the current one is very high risk. So other lower risk concepts need to be explored that also have like high redundancy and are more efficient. 500 kgs of regolith sample return is a very high constraint. So probably for future studies, we can try to vary this amount of regolith sample to see how the mission changes, especially cost-wise. Then the cost of extracted mineral needs to be significantly greater than mission cost. So this also plays into different asteroids which have like other valuable materials such as gold and other platinum and things like that, but it could come at a delta V cost. And more asteroid exploration missions need to be funded before the actual asteroid mining technique happens, because the TRL for this overall mission is very low as it's not being done yet. Thank you so much. Yeah, so we would like to take any questions now.
Yeah, exactly. So if any questions, you can just drop down in the chat box or just unmute yourself and ask.
Yeah. So in one of the slides, it was mentioned that ISP value as 335.4 meters per second. Is that ISP or something else?
No, that is ISP. So ISP can be, shown in two ways. One is just seconds, but when we're using it in calculations, we need to convert it into meters per second. So we need to multiply that by 9.81, the gravity parameter of Earth. So in order to make things easier, that gravity parameter does not change. So even if the satellite is at, say, the Jupiter's orbit, it's still multiplied by 9.81.
Okay, all right. Because when people look at the rocket engines, if you mention it as seconds, it's very easy to comprehend or understand how efficient your engine is.
Yeah.
Okay, that's enough. And great job, great explanation, and great presentation.
Thank you.
Perfect. Do you have any other questions? Okay, cool. So looks like we don't have any other questions. So everyone, if you have any other questions, you can get in contact with the team. You can check out their websites and you can have a look at their work.